All right, welcome to ECE203, Biomedical Integrated Circuits and Systems. This is Lecture 2. Lecture 2 is going to be a little bit of a departure from what you're going to see for the rest of the class. And it's going to be quite different than what you typically see in normal, certainly circuit design classes and most electrical engineering classes. We're going to talk about, of course, the physics of MOSFETs, which is a very conventional topic in electrical engineering, but also the physics of how neurons work. And the reason we're going to do this is it turns out that a lot of our circuits that we're going to build in this class are going to be inspired by how biology works. And so understanding how one of the principal compute elements in biology, neurons, operate, turns out to be very insightful and useful. Not only that, it also turns out that the physics of how MOSFETs operate, particularly in the subthreshold regime, turns out to be very similar to the physics of how neurons operate. So we're going to study this in this course, in this lecture. Now again, this is highly unusual of a topic to discuss in a circuits class. So if you're a little put off by the material here, don't worry, we'll get into circuit design and so on a little bit later on in the course. But I think this is a useful exercise, particularly looking at the nice analogies between physics, MOSFETs, and neurons. So at a high level, we can take a look at the difference between electronics, which are typically built in silicon, and another form of, say, computation that we could consider, and we call this ionics. This is what biology uses. Okay. Now in electronics, we call it electronics because electrons are the primary mode of passing information between various devices. In biology, that's accomplished not through electrons typically, but rather through ions. Okay, so in electronics, we get electrical signaling through semiconductor lattices and metals and so on. In biology, this is through ion transport in solution, not in kind of rigid structural forms. We have insulation in electronics by things like silicon dioxide, hafnium oxide, other high-K dielectrics. In biology, we typically use lipid bilayers as insulating materials. These are the cell membranes. In electronics, we have very high electron or hole mobility. In biology, mobility is much worse. Ions do not travel nearly as fast in solution as electrons do in semiconductor lattices. In electronics, we have very high dielectric constant oxide capacitance. Well, I guess I shouldn't say very high. We have reasonably high dielectric constant. In biology, it's actually much higher. Biology, these lipid bilayers, the capacitive density, very high, very, very good. Electronics typically operate at high voltage. They have high currents to deliver high performance, whereas biology is very different. Biology operates on a power supply less than 100 millivolts. Typically, each element has very low current, picoamps of current between elements, and biology is three-dimensionally integrated. Whereas electronics and silicon is usually 2D, planar integration, a little bit of 2.5D, maybe we stack dies on top of each other, but real 3D integration really isn't happening in electronics today. So at a high level, the differences between electronics and ionics is that in electronics, we typically operate at high speed. Our processors are at gigahertz of frequencies. We use very highly centralized von Neumann type of architectures for precise digital processing typically. Whereas in ionics, most of the brain, for example, operates at very low speeds. We're talking about kilohertz, effective bandwidths of our signals. But rather than having a centralized CPU core, we have massively parallel processing. Memory is embedded right next to the computational elements. It's very highly efficient, as we'll discuss a little bit later. So it's very, very different than how electronics compute, but very powerful in certain types of computing problems. So before we get much more into the ionics, let's make sure that we're all on the same page on electronics. And specifically, let's make sure that we all understand, NMOS and transistor, NMOS and PMOS transistor cross sections. Of course, this is an NMOS transistor on this side. This is a PMOS transistor. These are both in a bulk PMOS substrate here. The NMOS is technically a 4-terminal device. We typically draw it as 3 terminals, the gate, drain, source, but we do have that that bulk terminal that actually we may end up using fairly significantly in this class. If we neglect to draw the bulk terminal, we typically just draw the transistor like this. Sometimes people will also draw the transistor like this, although it's not very fashionable these days. The PMOS transistor looks something like this. Again, this is the gate, the source, the drain, and the bulk. Sorry, that looks like a P. That should be a D. In digital design, we typically forego the arrow notation and use the bubble notation. If we want to draw the direction of the bulk, we typically draw it like so. Okay. So this should all be a very clear review for the folks of you who are circuit designers. Now, if we take a look at the IV curve, so in other words, if we plot the drain current versus the gate to source voltage, we typically get a curve that looks something like this. Below VGS, or below the threshold voltage of the transistor is effectively off, and above that threshold voltage, the current starts to increase by some manner, and how much it increases depends on if we're in velocity saturated mode or else. Okay, now this is not the best picture when we want to talk about low power biomedical circuits, energy efficient computing elements, neuromorphic computing, etc. Because the assumption that current is zero below the threshold voltage, that works fine for digital circuits. It turns out it's not very appropriate for low power analog circuits, or for that matter, low power digital circuits. So if we replot this same curve here, but instead plot the y-axis on a log scale, what we find is that current below the threshold voltage is not zero, but rather it's an exponential function. Okay, so on the log scale, the curve looks something like this. Okay, so we can say here is that in this region we have low voltage, we have low current, and therefore low power. So that's great. So we call this the sub-threshold. I'm going to abbreviate this as sub-VT, but it's called sub-threshold region is an important regime of operation of our transistors that we're going to use heavily in this class. Okay, so of course, low voltage, low current, that means low power. That's great. Of course, there has to be a trade-off. There's nothing that comes free in life, and usually that involves slightly lower performance, typically in terms of speed, not necessarily in other aspects such as noise. We can be very clever about how we work with noise and subthreshold. That we'll discuss later on in this course. So what I'd like to do now is we have a little bit of a contrast between electronics and ionics. We have a very basic understanding of how MOSFETs operate. I would like to introduce the physics of subthreshold behavior of MOSFETs, but I'm going to do this in a very different way than is conventionally done in normal textbooks. In fact, in most undergrad courses, we don't really talk too much about subthreshold. In graduate courses, it becomes very important, and we do, but we typically don't really get too much into the physics of it. So we're going to do this in this class. Now, what follows, and there's a very clear warning here, is oversimplified analyses. Okay, so this isn't, we made a few liberties and some assumptions in the analysis, but to first order, I think this nicely explains at an intuitive level what's going on in the physics of subthreshold MOSFETs, and for that matter, cellular biophysics and neuroscience elements like neurons. So let's start with some very basic physics. Let's take a look at, say, for example, particles in the Earth's atmosphere. Or maybe these are charged particles in an ionic solution, or maybe electrons or holes in a transistor. Now, in either case, we say that these are particles. They have some distribution in space. And it doesn't matter if these are gas molecules, ions, or electrons. They all traverse their environment with a random walk. Which means essentially they experience Brownian motion. Now we're going to discuss the statistics of the Brownian motion a little bit more detail when we get into descriptions of noise. But for now, let's say if there's no force being applied to any of these particles, then they're just going to kind of move around, randomly bump with some amount of thermal energy. Okay. If the distribution is constant, there's no external force, the net current is going to be 0. So now let's add a force to this picture. Okay, so for example, maybe this force could be, an electric field, maybe it's gravity or something like this. Okay, so we have some force that's being applied to these particles. All right. Now, what I'm going to do is I want to derive the effective velocity that these particles are going to experience on average. Okay, and to do that, I'm going to define two parameters. One is T sub f. This is the mean free time, the time between particles colliding with each other. And H sub f is the distance that these particles are going to cover within the mean free time. And an assumption I'm going to make here is that immediately after every particle collision, their initial velocities on average are going to restart at 0. Okay, so let's take a look at this. We say H sub f is going to be the double integral of the acceleration with respect to time, which is the integral of acceleration times time with respect to time, which is of course 1/2 ATF sub f. Let's make that a little bit more pretty of a sub f there, squared. Okay. Which is equal to 1/2 f over m t sub f squared. Okay, so we say that the drift velocity, because of the force acting upon these particles, v sub drift, and this is going to get a little confusing. I'm going to try and make lowercase v's have a little squiggle on them to differentiate them from uppercase v's, which is going to be a voltage. So lowercase v in this lecture is going to represent a velocity, and uppercase v is going to represent a voltage. Hopefully it won't get too confusing, and context will be appropriate. So we can say that the drift velocity is the distance covered by the particle over the time that distance is covered by. So we can say that's 1/2 f over m t sub f. Okay. For a charged particle, for example, an electron or ion, we say that the force is equal to the charge times the electric field, okay, which means that V drift is going to be equal to 1/2 Q times E times T sub F all over M. Okay, so part of this formula should look fairly familiar to you, particularly if you've studied semiconductor physics. Okay, particularly these parameters here. Now think about this before I draw the next symbol here. What is this parameter? Well, it turns out it's mobility. Okay, so this is mobility. So in the previous slide, we had discussed what happens to these particles if there's a force applied to them, and we were able to derive what we call the drift velocity of these particles. Now, if we were to remove the force from the picture, but instead rearrange the particles so that there's a spatial distribution of these particles, we will also get some sort of velocity. So let's imagine that we have two regions here that we've divided our particles into, and there's much more particles on the left than on the right here. Okay, so one question we can ask ourselves is, will there be net current or a net flow of particles across the barrier? Okay, now there's no force being applied here, but it turns out the answer, despite there being no force, is still yes. Okay, and it's actually very interesting if you haven't studied this before. Purely by random motion, half of all particles on each side will move to the other side. And I can say this assuming that each of these regions has a distance h sub f. Okay, so that's interesting. So let's imagine that on this side we have n particles, and on this side we have n plus delta n particles. So what this means is that from right to left, we're going to have n over 2 particles moving this way. From left to right, we're going to have n plus delta n over 2 particles moving in that direction, which means that we have a net flow of delta n over 2 particles going in this direction. Okay, so this is the net flow. The net flow from high to low density. Okay, all right. Now let's create another parameter called v sub capital T, and we're going to call this the non-average initial velocity. Okay, so what we can say here is that the diffusion velocity is going to be equal to delta n over 2 times v sub t over n0. Now in this case, n0 is the total number of particles. Okay, so I guess in this specific example it would be 2n plus delta n. Okay, so then what we can do is we can say delta n is equal to dn dh times h sub f, and we can say v diffusion is going to be minus 1/2. Minus just becomes we're going from net flow from high to low density, just to keep the sign correct here. dn dh times v sub t, t sub f, v sub t over n0, which is all equal to minus 1 over 2n dn dh t sub f v sub t all squared. Okay, so we went through a little bit of math here. Where the heck are we trying to go with this? Okay, so first of all, what we've done in the previous slide was we created a expression for the drift velocity of particles when a force is applied. We've in this slide we've created an expression for the velocity of particles just basically due to spatial distribution, which will cause diffusion. Okay. Okay, so we can say we have the drift velocity, and at thermal equilibrium, we can say that 1/2 mvt squared is equal to 1/2 kT, which is just the thermal energy. Okay, so with this we can say Vt squared is equal to kT over m, which means that the diffusion velocity is equal to minus 1 over 2n times dn dh times t sub f times kt over m is equal to, we can simplify this a little bit, and what I'm going to do is I'm going to pull this factor of 2 out, and I'm going to pull this parameter out here. And please take a moment to just stop and think just for a second about what this might be. Indeed, that is actually the diffusion constant minus d, 1 over n dn dh. Okay, so let's just notate that here. This is the diffusion constant. Okay, so just out of curiosity, if we compare this to drift, what we find is D is equal to KT over Q times mu. And this should also be a familiar relation. This is the Einstein relation. Okay, so where the heck are we going with this? This is a little bit of a random walk, for lack of a better word, but it turns out that this is very useful, again, when describing subthreshold MOSFET performance, as well as ion transport across neurons, for example. So let's take a look at this seemingly unrelated example. Let's take a look at a particle in the Earth's atmosphere. Now, this particle will experience two different mechanisms by which it will tend to derive some velocity. One is, of course, drift due to gravity. W here, we're going to call this is the molecular weight. So we have some drift velocity that's going to happen because of gravity. We also are going to have some diffusion of particles that are going to want to go towards the surface of the Earth, because there's just, well, there's more, or they're going to tend to want to go away from the surface of the Earth, rather, because there are more particles on the Earth than in the atmosphere. Now, of course, the world exists today. It hasn't blown up, so we must have some equilibrium happening here. At equilibrium, drift and diffusion must cancel. And so we can say 1 over n dn dh kt is equal to minus w. That's the molecular weight being applied here. So we get an integral from n0 to n. n0 is just a reference point. 1 over n kt dn, which is equal to the integral of minus w dh. So we're integrating essentially from some density at a reference height to the height that we're interested in computing this for. And we get kt natural log of n over n0 is equal to minus wh. Let's just make a little note here. N0 is the density at reference height. Okay. So we can say that n, the density at a certain distance above the surface of the Earth, is equal to n0 e to the minus wh over kt. Okay, so I'm going to box this here. This is really what we've been trying to do all along here. This is an expression that describes the density of molecules per unit volume in the atmosphere at a certain height above the surface of the Earth. This is an exponential relationship, which of course means that the density it's much stronger at the surface of the Earth than away from the Earth. And this is an important exponential distribution that we refer to as a Boltzmann distribution. Okay. So it turns out that Boltzmann distributions are found everywhere. Okay, so they can be used to describe the density of electrons and holes in a MOS capacitor, for example. They can be used to describe the voltage-dependent conductance of an ion channel in a molecule or a neuron. They can be used all over the place. Okay, so we're going to use the Boltzmann formula we just derived here to derive subthreshold conduction in a MOSFET, and also we'll also use it to show channel conduction in a in a neuron, rather. So let's take another analogy here in order to help us describe how Boltzmann relations can be used to describe the conduction of a MOSFET, a subthreshold MOSFET. Okay, and so to do so, let's take an analogy and tell a little bit of a story. Okay, so there's this town. They have a big lake that accumulates a lot of water. All right. Now they wanted to construct a dam in order to store some of this water for periods of drought, so they can always have a nice water supply. And what they found is that after a big rain, when the dam was almost full, the engineers would notice that the water level would go down fairly rapidly. Okay, so they found this a little puzzling. They searched the dam, they didn't find any leak or anything like this, but they only noticed that this happened when the dam was near capacity. But when the dam water level was much lower, they found that there wasn't a lot of, the rate that the water went down wasn't occurring nearly as fast as when it was much higher. Okay, so the question that we are trying to ask ourselves is, water only goes down after a big rainfall. And the question is, why? Okay, and so the answer, you have to think a little bit outside the box here, but the answer is that this effect is loosely real, and it's really because of diffusion of water vapor. And what I mean by that is when the dam level is very low, then the water vapor is going to have some sort of Boltzmann distribution. It's going to be very dense right near the surface of the water, and it's going to exponentially decay away from the water. So we can describe this by some sort of Boltzmann distribution, I naught, some reference point, e to the minus w phi. Phi is the distance from the top of the dam there, over kt. And if we plot this, plot phi versus the natural log of the current here, what we'll see is an exponential function. So this is an exponential Boltzmann relationship. Okay, so what ends up happening is that the amount of water vapor close to the surface of the water is very high, but it exponentially falls off as you go away from the surface of the water. And so what ends up happening is when the dam level is very low, very little of that water vapor is present above the lip of the dam to get over to that other side. Okay. However, after a rainfall, the water level is very close to the top of the dam. Therefore, there's a lot more water vapor that's eligible to essentially go over the lip of the dam and run off to the other side. Okay. So this is effectively an analogy for subthreshold leakage. We have currents flowing through a transistor that, the transistor voltage is below VT. There shouldn't be any current happening, but it still does, and it responds to an exponential behavior. Okay. So the engineers in the town decided to get creative. Okay, so they said, we don't like it when the dam gets very full and then we lose a bunch of water. That's really not what we want to happen. We want to keep all of that water. So they said, why don't we just construct a taller dam? Well, that's expensive. You have to get all these materials, construct a taller dam. All we're really trying to do is block water vapor, not actual, high density water. So why don't we build just a little hydraulic barrier? It can be thin and light. As long as it blocks water vapor, we're all good. Okay, and so effectively what we can do is we can modulate the height of this barrier from some other reservoir, some other energy source, and use it to control the rate of diffusion of water vapor molecules going across the dam. So what we can say here is that the current is going to be some reference current I naught, e to the minus w, h1 minus h2 over kt. Okay, or in other words, I1 is equal, or I is equal to I1 e to the v1 minus v2 over kt. This would be in voltage and electrical parameters. So what we're saying here is that the rate of diffusion is now being controlled by another variable. So this is very similar to a subthreshold, again abbreviating sub-VT, subthreshold MOSFET. All right, so let's take this analogy one step closer to being more realistic. So let's imagine now that we have a source and a drain of water molecules, or as the analogy goes, electrons. So we can say that this is the water, these are the water vapor. Okay, and we have some way to control the height of the dam. All right, now when the dam is high enough such that there's no direct path for water to go from one side to the other, we say that the flow mechanism of water vapor molecules, or electrons in a subthreshold MOSFET, is a diffusion mechanism. Okay, so as in the hydraulic analogy, we have an exponential dependence on, in this case, I'm going to call it the gate voltage. And what I mean by that is if the gate voltage in this case is very low, and in this analogy that means the barrier is very high, there's not going to be a whole lot of vapor that has enough energy to cross that barrier. But as the gate voltage starts to increase, or conversely the barrier starts to decrease, then there's a lot more vapor molecules that are able to get over there. Now, the other thing to consider is that since VDS is small, that is the difference in water levels on either side of this barrier is low, this means we have a low electric field and low drift. So we're essentially trying to describe this in a scenario where we are diffusion dominated, not drift dominated. Now, as soon as that gate barrier or the dam height starts to get low enough, to the point where you do start to get a little bit of possibility to have some flow of actual water, not just vapor across, that's what we would call, at least in a MOSFET analogy, moderate inversion. Okay, so weak inversion is our subthreshold. Moderate inversion is when VGS is just about equal to VT. So this is the analogy in subthreshold. In above threshold, we have a flow mechanism that's based primarily on drift. Okay, so in the off mode, when VGS is well below VT, we have our water vapor molecules. We call this the cutoff mode. It's really subthreshold mode. We say that there's very little current flowing through the channel. We understand now that there is actual current flowing through the channel. It's an exponential amount of current, and it is there, but at a loose level, it's zero. Okay. Now, if we go ahead and lower that dam height so that there is a direct connection of water between the two different reservoirs, then we can get flow of current. Now, if the reservoir levels are about the same on either side, we say that the transistor is on and linear, i.e. VDS is small, so we're effectively in the triode mode of operation. So there can be current. It depends on the levels of the various of the source and the drain. Now, if for example the one of the reservoir levels starts to go down, then we can say it's on, and in this case still pretty linear. Now, in the case where the one of the reservoir levels is so far down that there is only so much water that can get from one side to the other, then we can say that we are in the on and saturated mode of operation. Okay, so that was again a simplified analogy. Let's go ahead and write some expressions that is going to describe how this would work in an actual subthreshold MOSFET. Okay, so first cross-section of the MOSFET. We looked at this earlier. We'll also describe the left region as the source region, the right region as the drain region, and as we increase the gate voltage, we're going to say we're lowering an energy barrier in order to facilitate larger amounts of conduction. So in this case, to derive some expressions, we can say let's let n sub 0 be the carrier density in the channel at the Fermi level. Okay, so if we know the energy barrier from the source to drain, or sorry, the source to channel and the drain to channel, we'll call this phi sub s or phi sub d, then we can calculate the source drain carrier density using a Boltzmann distribution. So the source drain, the density at the source depends on the gate to source voltage or the energy barrier, I guess, phi sub s, in our familiar Boltzmann distribution. Similar story at the drain. Now this energy barrier is modulated with the gate to source voltage. We'll call this phi naught plus Q times Vg with respect to either the source or the drain, where phi naught is the built-in or the nominal potential barrier. And so then we can write these expressions down here, which effectively says, relates the gate to source voltage to the energy or the carrier level at the source terminal, for example. Okay. So now that we have these expressions here, of course, we can say VGS is just VG minus VS, just to be extra clear, and these should be uppercase V's to distinguish them from velocities. We can now compute the gradient density along the channel. Okay, so what we say in order to do this is that current has to be the same at all distances in Z from 0 to N. All distances Z, where Z equals 0 is the start by the source here, and Z equals L is the end of the channel. Okay, so what this means here is that N must be a linear function of Z. Okay, so dN dZ must be a constant then, and we can just say it, well, it's the density at the drain minus the density at the source over the channel length, right? Now we have expressions for density of source and drain based on the expressions derived in the previous slide, so we can substitute those in here, and then we get the following expression. Now this is dN dZ, that's not a very useful parameter, so we want to convert that into current. We recall that current is the total charge times the diffusion velocity. In this case, we're in subthreshold, where the diffusion velocity was derived earlier. So we can say the current density, where we normalize by the width of the transistor, is effectively equal to this formula here. Okay, so it's still a little bit complicated, not quite what we were hoping for. Let's make a few further simplifications. So first of all, we like to normalize by W. Current density, you know, when we talk about transistor physics, it's often useful to talk about current density. The other thing I'm going to do is I'm going to take this whole parameter here. This is basically just a constant. I'm going to lump W into this, and I'm going to call this I naught. Okay, I'm going to call this some reference current level that is a constant based on the geometry and the parameters of the semiconductor materials. Okay. Furthermore, just to simplify the analysis here, I'm going to set Vs is equal to 0. I'm going to say Kt over Q is equal to phi t. By the way, this should be a familiar parameter to you. This is the thermal voltage, which is roughly 25 millivolts at room temperature. And note, I'm going to use phi t here. Just some texts use Vt. I find that very confusing because VT, is that the thermal voltage or is it the threshold voltage of the transistor? It's not really clear. In this case, we're going to say VT is the threshold voltage and phi t is the thermal voltage. So everything should hopefully be fairly clear. So Q should be negative. So let's just flip the sign and we get a expression that looks like the current through the subthreshold MOSFET is I naught e to the VGS over phi t times 1 minus e to the minus VDS over phi t. Okay, so those of you who have studied MOSFET physics before should find this formula to be very familiar. However, I'm going to say, is this correct? Well, of course, if I'm writing, is this correct on the slide and asking it, the answer is probably going to be not quite. Okay, and we're missing one key thing here that is very important for MOSFETs in particular. And this key thing, it's a simplifying assumption that we made along the way, is that the gate voltage directly affects the channel potential. And it turns out that's not quite true. And the reason for that is effectively because of depletion region capacitance that arises because of the doped channel region of the device. So when the gate voltage is 0 and the substrate is 0, the surface potential is 0, everything's 0, okay, fine, everything's all 0. Now when we start to increase the gate voltage, in this case labeled as moderate VG, then what ends up happening is if there were no depletion region, then the surface potential would basically just mirror the gate voltage. But it turns out that there is, the substrate is doped, in this case it's doped P, and so when we apply a positive charge to the gate, then we effectively get attraction of electrons to the surface of the channel region here. This leaves non-mobile dopant atoms open in a depletion region area here. Okay, so what we can do is we can effectively model this as a series capacitor type of structure here. Okay, so we say that this is VG over here. We call this COX. This is the gate oxide of our the gate oxide between the gate and the channel. We say that this here is the surface potential, and I'm sorry, that shouldn't be necessarily grounded, and this here is the depletion, the capacitance of that depletion region, and then this finally is the bulk, and I guess technically we typically tend to ground that bulk. Okay, so what this means is when we do change the gate voltage of our MOSFET, the surface potential, it certainly does change, and it's proportional to the gate voltage, but it's not directly proportional. There's a factor there that we have to take into consideration. Now we call this this factor kappa. It's effectively the capacitive divider between COX and C depletion. And we have to incorporate that into our subthreshold MOSFET formula. Now, some people like to use kappa. More typically, we tend to use 1 over n, where n is a subthreshold coefficient. And so basically, the surface potential is the gate potential times kappa, or the gate potential divided by n. Now, in most CMOS processes, n is somewhere like 1.4, something like this, which means that kappa is usually somewhere around 0.7. Okay, so this means our subthreshold formula ends up being I naught e to the VGS over n phi t times 1 minus e to the minus VDS over phi t. Okay, and I'm going to box this, nice big box. This is a very important formula. We're going to use this throughout the course very significantly. Okay, so we have our subthreshold formula here. What does this mean in practice? What does it look like? So let's first of all plot the log of the drain to source current versus VGS. I guess we've technically done this before, but now we can do this a little bit more precisely. Okay, so we say here is that in the subthreshold region, we are exponential. So on a log plot, we basically have a straight line. And then as we exit the subthreshold region, we go into the it'll be quadratic or linear depending on what type of MOSFET model we have here. And we can say that, well, if this is an exponential on a log plot, it should be linear. We'll have some sort of slope here. Let's call this S, in this case 1.4 for N equals 1.4 for a MOSFET. We say that S is the subthreshold slope. And just beware, we call it a slope. Usually slope is dy dx, dy over dx. In this case, our slope is dx over dy, so it's a little bit different units than you're used to. Just be aware of this. People get messed up in assignments and exams oftentimes about this. In this case, we define it as n phi t times the natural log of 10. For n equals 1.4, this is 80 millivolts per decade. So see the units are the reciprocal of what we tend to expect when we talk about slope. Okay, so this is for a MOSFET. One question is, n equals 1.4 is typical. What would be the best? Well, in our prior formula, we said that we kind of forgot about n in the first case. Basically we meant that n is equal to 1, which means that we don't have this capacitive divider thing happening. Now, if we didn't have that, if n were equal to 1, then the plot would look similar. It'd still be exponential, but it would just have a much higher slope. Okay, and then we'd trail off into the above threshold region. So if we call this the slope when n equals 1, which is the ideal case, then it's equal to 57 millivolts per decade. N equals 1. Okay, so what this means is that n limits the subthreshold slope. Now, the question is this good or bad? Okay, and think about it for a second. Maybe even pause the video just to think about it for a second. Is this good or bad? Well, it turns out that in almost all cases, it's bad. Okay, so for example, maybe we want a better ion to I-off ratio. We want a small n. For example, when we want the switch to turn off, we want very little current flowing through that transistor. When we want it on, we want lots of current flowing through that transistor. So a steeper subthreshold slope will be better. Okay. The other thing I want to mention is note the similarity to the conduction of a BJT, right? We say that IC is equal to IS, e to the VBS over phi t. So it's exactly the same, except we don't have that factor n in the BJT because there's not that capacitive divider. So what that means is technically BJTs, at least in the subthreshold region, they have a steeper subthreshold slope, which often means they have better performance. Okay, so one question you might ask is, well, why don't we just use BJTs? For very high performance systems, we do. Actually, the reason we emphasize CMOS and MOSFETs is because MOSFETs are so much better at digital logic and high density integration and so on and so forth that they become essentially a de facto choice, and you need a somewhat exotic technology that incorporates BJTs alongside MOSFETs so that you can do your digital and your analog and your RF circuits together. I would say most modern integrated circuit design today, except for the very high performance stuff, is done exclusively in CMOS. And that's very true of most biomedical applications as well. So far we've spent a lot of time focusing on VGS. What about that parameter in VDS? Okay, so it's there in the subthreshold formula. It's right there. E to the minus VDS over phi t. So there's no subthreshold coefficient for VDS. So if we plot IDS versus VDS, what happens? Well, when VDS is very, very small, then E to the 0 is basically 1. 1 minus 1 is 0, so current is 0. Okay, so that's good. When VDS is 0, we shouldn't have any current flowing through the device. That makes us happy. Now, as VDS starts to increase, that E to the minus VDS over phi t term is going to start to get very small, to the point where VDS is much larger than phi t, that parameter basically becomes 0. And so effectively what ends up happening is we have a somewhat linear region and then we saturate. After we saturate, doesn't matter if VDS increases, we basically don't get any increased drain to source current. So we effectively get a saturation region within the subthreshold region, just like we do in the above threshold region. And we can say that this transition from the linear mode versus the saturation mode happens at roughly 4 phi t, or about 100 millivolts at room temperature. Okay, so that's for one value of VGS. Of course, we can have a family of curves here for different values of VGS. So as VGS increases, the amount of current flow through the devices increase. So this is really interesting. This is different than above threshold MOSFETs, where the region between saturation and non-saturation depends on the bias level of the device. And of course, there's very good physical reasons for that. But in subthreshold, making sure that you're in saturation is actually a little easier. All we have to do is make sure that our drain to source voltage is larger than about 100 millivolts at room temperature, and we're in saturation. Now, it also turns out that 100 millivolts is usually quite a bit lower than the amount of drain to source voltage that we need in above threshold, which means that we can tend to bias our analog circuits, for example, in the subthreshold region with much lower supply voltages than we need in above threshold, while still keeping everything in saturation. So this is a nice power benefit of operating in subthreshold. Not only are currents low, but we can also tend to work with much lower supply voltages. So if we could summarize the behavior, we have a plot here pulled from the Sarpeshkar book. We basically see in subthreshold, we sometimes call it weak inversion. Subthreshold is what we've been describing it as so far in this class. We basically get a fixed saturation point of about 100 millivolts or so. And then when we start to go into moderate and then strong inversion, or in other words, above threshold, we'll say above VT over here, then that point where we stay saturated starts to strongly depend on VDS. Okay. So as I said, this is an important power benefit of subthreshold operation, but of course there's always a trade-off. There's no free lunch. It does come with some particularly speed trade-offs. So if we take a look at the above threshold behavior, we of course have our exponential law behavior. Again, this is plotted on a log scale here. When we start to get into above threshold, we end up getting square, that's not a very good AR here, square law behavior. Now, of course, that's assuming we're not velocity saturated and above threshold, which would make this more like a linear law, but that's okay. So what we say is that for the same size of transistor, we get much larger current in above threshold than in subthreshold. And of course that makes sense, but the key assumption here is the same size transistor. We don't necessarily have to use the same size transistor. We could potentially, for example, operate in subthreshold with the same amount of current as another device operating in above threshold if that device happens to be very large. Okay, and we'll get into some of the reasons for this and the insight into that later on in the course. The other thing I want to mention is that in above threshold, unlike in subthreshold where current is dominated by diffusion, in above threshold current is dominated by drift. So this is a nice analogy. If you want to learn a little bit more about this, you can take a look at the Sarpeshkar book. It's a very interesting text that describes some nice intuitive physical analogies and constructs of what happens in subthreshold MOSFETs. This is a picture here depicting essentially the reason for the subthreshold coefficient due to the depletion region in the subthreshold region. But then what's interesting is that in above threshold, we effectively don't get this behavior anymore because the surface potential gets pinned to a certain value when it's saturated with excess electrons in the depletion region, and conduction from source to drain becomes a lot easier in this condition. So again, if you want to learn a little bit more about this, the Sarpeshkar text, very, very interesting read if you want to explore a little bit more. Now, of course, we wouldn't have a complete circuit design course without also showing the equations for above threshold MOSFET conduction in the saturation region. In this course, we're going to use the usual formula, 1/2 mu Cox W over L times VGS minus VT squared. Again, we're not going to assume velocity saturation. We'll just assume that it's in the quadratic law. And then, of course, we also have the linear or the triode mode, where we have the linear dependence on VGS. The Sarpeshkar text also has an interesting kind of intuitive transistor model. We have diffusion currents that happen because of in the subthreshold region. We have drift currents that happen in the above threshold region. We have our gate oxide here, and the transistor is a kind of a distributed transistor here. This is the channel, effectively, this node in the middle here. This is the substrate. The junctions are modeled basically based on diodes, and it kind of gives a nice intuitive feel for how a transistor works in all regions of operation. So again, if you want to learn a little bit more about this, I recommend taking a look at the Sarpeshkar text. Okay. All right, so that was a very quick overview of how we can characterize the transistor behavior in subthreshold and in above threshold. Useful to contrast the two modes of operation between each other just a little bit. So in subthreshold, the saturation current is exponential in VGS. Okay, versus above threshold where it's quadratic. The saturation voltage, the drain to source voltage in subthreshold is always 100 millivolts. Of course, at room temperature, it doesn't really change, whereas in above threshold, you really need to be careful about the bias region to make sure that you're going to be saturated. In subthreshold, current flows by diffusion versus drift in above threshold. Subthreshold is typically good for low power systems versus high speed systems in above threshold. We're going to get a little bit more into power efficiency and so on and so forth in later lectures, but it turns out that in subthreshold it's more constant with current than in above threshold, and in fact subthreshold is more efficient, at least in terms of noise and gain, in subthreshold than it is in above threshold. Of course, in subthreshold, we can work at lower supply voltages because of the lower requirement on the drain to source saturation voltage. And it also turns out that the exponential behavior of subthreshold is beautiful, and the math works out so much more nicely than the messy quadratic equations for the above threshold transistors, that not to mention are also fairly inaccurate. It turns out that the exponential behavior in subthreshold is fairly accurate, whereas the quadratic, in modern transistors, it's way off. Okay, but the punchline here is that in subthreshold, it's usually much more suited for kind of slow and parallel type of architectures, which again is much more like how the brain works, rather than in above threshold, which is much better suited for fast and serial type of architectures. So when we go ahead and make our say biologically inspired compute engines, it's likely that we'll end up doing it in subthreshold rather than above threshold, at least for most of the functions. Okay, so this table just kind of reemphasizes the point I'm trying to make here, is that if we're going to try and make electronics look somehow like ionics, we need to exploit regions of operation where we can build low voltage, low current, massively parallel types of systems. And really that sounds very much in the wheelhouse of a sub-threshold design rather than an above-threshold design. All right, so as I mentioned earlier, and nature is essentially the world's greatest engineer. She has created some phenomenally complicated organ structures and animals and so on and so forth. And we as human engineers really ought to learn as much as we can from nature, because there are very, very clever ways that biology has tackled problems that I think we can really learn a lot from. Okay. In fact, even things like computing, like image recognition, for example, the human brain is far, far better than even supercomputers at doing things like image recognition. And the human brain is much smaller, much more efficient, et cetera, et cetera. Okay. So as a biomedical circuit designer, I think it's important to understand at a very high level, at least, how biology works for two reasons. One is that it helps us when we actually build interfaces that interface with biology. So if we're trying to, read how the heart is working or trying to read brain waves, it really does help to, know how those brain waves or heart waves are being created so we can build an interface that captures them with the appropriate resolution and dynamic range and so on and so forth. The other side of this is more biomimetic design, or bio-inspired design, where we look at biology, see how it solves a similar or related problem, and see if we can apply similar constructs to the way that we solve our own problems. So this is somewhat of an old comparison, but I think it's still very appropriate. This is an Intel Itanium processor that was released in 2002, so this is quite old, but its power consumption and number of ops and stuff is somewhat still similar to what you can get from today. And if we compare that to the human brain has many billion of neurons inside of it. It has trillions of synaptic connections between these neurons. It has 10 to the 15 synaptic operations per second at an average of 1 hertz of a firing rate. We have 10 to the 10 I/O, which is a very, very large number. And importantly, the brain only consumes about 25 watts, and it's just really phenomenally powerful when it comes to certain types of tasks, particularly pattern recognition type of tasks. So the lesson here is that silicon technology is approaching the raw computational power and bandwidth of the human brain, but it's still doing it in serial, linear, von Neumann type of architectures that is good for certain things like number crunching and so on and so forth, but far less suitable for things like pattern recognition, for example. Okay, and so as a circuit designer, it is very useful to try and understand how the brain works. So here's just as another example. This was put together by IBM, but basically trying to compare the computing efficiency and the computing density of ops per second per liter, something like this, of supercomputers and biological brains. And you can see certainly in terms of efficiency, but also in terms of processing capability, biology has electronics beat by a mile. And so this is really a big driver in the industry today, particularly with a lot of work going on in machine learning and artificial intelligence and so on and so forth, is how can we build circuits that start to replicate the behavior and performance of biological brains. So let's take a slight change of direction here and understand a little bit more about how neurons work. Okay, so let's get inspired by analyzing the behavior of a neuron. So here's a kind of a cartoon description of what a neuron looks like. So the neuron is the actual cell. A dendrite is the connections that input into the neuron body. Basically, it's the input devices into the neuron. An axon is the output of the neuron. It will transmit electrical pulses along its length to other cells, which eventually split off into dendrites into these other cells. And the dendrite or the axon neuron interface is what we call a synapse. Okay, so the synapse is effectively where the actual interface occurs, and it's a non-conventional interface, at least related to electrical engineering concepts. It's not a direct electrical interface, but it's kind of a biochemical interface with molecules called neurotransmitters, which facilitate transmission of information. We're not going to get into neurotransmitters too much in this course. So it turns out that neurons communicate very, in a way that we can model with electrical circuits, and a way that as actually electrical engineers I think we can stand and appreciate. Okay, so the cytoplasm, or the fluid inside a neuron, has a pretty high internal resistance. It's an ionic solution, just like Gatorade or something like this. It has a certain conductivity, but it's certainly doesn't compare to gold or silver or copper or something like this, right? In addition, the neuron also has a fairly large membrane capacitance. It has a lipid bilayer membrane that has a effective capacitance between the inside of the cell and the outside of the cell. Okay, and so when a neuron wants to communicate with another neuron, what ends up happening is it creates an action potential. So it depolarizes effectively its internal potential with respect to the extracellular fluid, or the fluid outside the cell. This causes a spike that then should transmit itself across the length of the axon towards the input to another neuron. Okay, and because the intracellular fluid is high resistance and there's large capacitance from that lipid bilayer membrane, we basically get very large RC losses. Okay, so the length of this axon effectively looks like a distributed transmission line, a distributed RC transmission line specifically. Okay. Now, nature realized this. Well, I don't know if realize is the right word, but understood this and created a sheath type of layer, which effectively serves to reduce the capacitance between the axon and the extracellular fluid to decrease the RC losses, if you will. The R doesn't change, but the C does get changed very significantly. In addition, axons also have mechanisms to do active amplification or buffering, basically like digital logic gates. So this is pretty cool, actually, how this works. Okay, so again, we could have a whole course studying the cellular biophysics of how this works, but for the moment, let's just imagine that this is a distributed transmission line. We have repeaters that go here occasionally that help to keep the signal propagating along. So let's introduce a model of the axon itself, and we can think of this as the power supply of the neuron. Okay, and how this effectively gets established is that within the inside of the axon, and in this case we're going to go through an example of a giant squid axon, and this is just for classical reasons. It was one of the first animals that were really experimented with at depth to really understand how these neurons worked. What ends up happening is you get these proteins. Okay, so this protein here, this is essentially a battery-powered ion pump. So what happens is it effectively takes potassium ions from outside of the cell and actively pulls them inside the cell. And similarly, it actively takes sodium ions from in the cell and actively pushes them out of the cell. So this is a pump. We get drift because there's an active force being applied here of ions. And this is being powered by ATP. Okay, so that's where the energy source comes from. And so what this does is, if you take a look at the concentration of potassium ions outside of the cell, that's at, say, for example, 10 millimolar per liter, because of this ion pump, we get a much higher concentration of potassium ions inside the cell, 400 millimolar per liter. Now, of course, that can't happen continuously, or the ion will, or the cell will blow up. So we have to have some mechanism for ions to diffuse back. And so we have these ion channels that facilitate diffusion. Okay. So let's just fill in some of the other numbers. The sodium potential outside is 460 millimolar per liter. Inside it's equal to 50. Outside chloride is 540. Inside it is 40. Okay, and just to be clear here, this is the lipid membrane, or the capacitance between the outside. Okay. So clearly we have some sort of Boltzmann-like model that's going on here. We have an active pump that's applying a drift of ions, and we have diffusion of ions going out the other way. So recall from our example on the atmosphere, we can say that N, or the concentration, is equal to N0 e to the minus WH over KT. Here, or in that case it was density, we're going to say the concentration inside the cell is going to be equal to the concentration outside the cell, which is going to be our reference point here, times e to the minus QV over KT. Okay, so what we can basically say is that the voltage is equal to minus KT over Q times the natural log of the concentration inside the cell over the concentration outside of the cell. Okay, so this is a pretty important formula here. This is called the Nernst potential. Okay, now one note here, be careful of the sign of Q. Okay, because unlike in electronics, in ionics, we can have both positively and negatively charged molecules. Okay. So this is the Nernst potential. If you were to stick an electrode inside the cell and outside the cell and measure a voltage, you would measure a voltage, and that voltage would nominally be equal to the Nernst potential if there were only a single ion species present. Okay, but that's not the case. There's multiple different ion species. In fact, there's more than I'm showing here, but these are the dominant ones. And each one is going to have its own Nernst potential. So what is the overall membrane potential? If we were to stick an electrode inside the cytoplasm and in the extracellular fluid, we would measure something, but what? Okay. So each ion species has its own Nernst potential. Each ion channel also has an effective resistance associated with it. Okay, so we can effectively say each of the pumps is basically can be modeled as a voltage source. The ion channels are resistors, and we can effectively build a circuit model that will describe the overall membrane potential based on the interaction between multiple different ionic species. Now, one further note is at rest, neurons have a non-zero potential across their membrane. So they have a non-zero resting potential. This means that neurons are polarized. Even when nothing's going on, they are polarized. Okay. So before we get into a little bit more details here, I'd like to just briefly describe, with a little bit of cartoons here, what these pumps actually look like. So this is an animation. Hopefully it's going to play on my slide here. Yes, there it goes. So here we get some sodium ions going in. We get a little bit of energy that ends up closing the pump so that the sodium ions can go out to the outside. Similarly, in order for the pump to reset back to its present state, it grabs some potassium ions and pushes that to the inside of the cell. So, I mean, this is a rough, crude cartoon of how this looks like, but I think you get the idea. So far what we've done is we've described the equilibrium state of the neuron. But how does it actually communicate? It doesn't just sit there and do nothing, right? It has to do something. And it turns out that neurons communicate with a hybrid analog-digital paradigm. And what ends up happening is it's really quite interesting. We've talked about action potentials. These are discrete all or nothing events. It's like sending a 1 or a 0 down a transmission line. It's completely asynchronous. Again, the axons have repeaters. This is kind of more the digital-like interface of neurons. But dendritic processing also involves small graded potential changes. These are spatiotemporal changes in synaptic behavior that subtly affect, the relative ability or desire of a neuron to fire their action potentials as well. So there's a little bit of kind of biasing going on here. So this is more like an analog kind of compute construct. We're not going to talk too much about this in this course. We're going to focus mostly on the action potentials. So it turns out that the ion channels that we see along the length of the axon are voltage-controlled ion channels. Okay, they look kind of like diodes, if you will. Okay, so depending on the voltage across the membrane, the number of channels that will be open versus closed will depend on the potential established across that membrane. Okay, so let's create a simple model here. Let's say that there are n total ion channels on the length of a membrane. NC are closed and N0 or NO are open. So the total number of channels is just NO plus NC. Now, in order to open a channel, we need to there needs to be a certain amount of energy exhibited here. So we're going to call this E sub t is equal to E sub 0 V NCQ, where E0 is the energy when V equals 0, and NC is the number of gated charges that will go through the membrane at once. Okay, so for example, in that previous ion pump, we could get 3 potassium ions that go through at once to 2 sodium ions, or sorry, other way around. So the distribution of open versus closed channels can be described by N0 over NC. This is equal to e to the minus ET over KT. And again, our friend Boltzmann here is here to greet us. The Boltzmann model works perfectly well here. Okay. So what we can do now is we can say that the number of open channels, the ratio of open channels to closed channels, we can do a little bit of algebra soup here, is equal to NC plus NO minus NO. We've just added 0 here. That's equal to NO over N minus NO, which is equal to NO over N divided by 1 minus NO over N. I'm just manipulating this formula, okay? So NO over N is essentially the number of open ion channels divided by the total number of channels, which means basically this is the probability of having an open channel over 1 minus the probability of having an open channel times, which is equal to the relation we had on the previous slide, e to the minus ET over KT. Okay, so PO is equal to 1 minus PO times e to the minus capital E sub t over KT. And just to be clear, this is the probability of an open channel. Okay. All right, so we can manipulate this formula a little bit more. PO times 1 plus e to the minus, minus ET e sub t over KT is equal to minus e to the minus e sub t over KT. So we can say that PO is equal to 1 over 1 plus e to the e sub t over KT. And therefore PO is equal to 1 over 1 plus e to the e naught over KT times e to the minus V n sub c over phi t. All right, so that's the probability of the number of open channels. We can say that the conductance, which we'll say is capital G, is equal to the number of open channels times the number, or the probability of open channels times the number of channels times the conductance of a single channel. So that's conductance of a single channel. Okay, which means that the conductance satisfies the following formula: n little g sub o times 1 over 1 plus e to the e o over kt times e to the minus v and c over phi t. Okay. So this looks somewhat similar, maybe a reciprocal, but somewhat similar to what the subthreshold behavior looks like. And so we're plotting conductance here. You know, if we plot a resistance, it would basically be the reciprocal of this, and it'd basically be the subthreshold formula. So this is really interesting. We're talking about the conductance or the resistance of a voltage-controlled ion channel, and we get a formula very similar to the subthreshold behavior of a MOSFET. Very interesting. Okay, but there's an interesting trick or catch here. Now, what's really amazing about the conduction of the ion channels here is that, of course, it has the exponential behavior that sounds very familiar to what we have in our subthreshold MOSFETs. But what's really amazing here is the subthreshold slope. So we're getting 9 millivolts per decade here for sodium conduction and 11 millivolts per decade here for potassium conduction. Okay, so that is far superior of a subthreshold slope than what we get in a subthreshold MOSFET or in a BJT for that matter. And so that's just, it's amazing that this happens. It's amazing that it also has to happen, it ends up happening at a power supply voltage that is far lower than CMOS. So the inherent devices are much have much better performance characteristics, and also end up being able to operate rather at much lower power and supply voltages. Interestingly enough, we also see some similar saturation behavior. That we've seen in MOSFETs as well. So that's pretty cool. So we can take an analogy of biology to electronics in the following manner. We said that cytoplasm was loosely something like a resistive wire. The lipid membrane was effectively capacitance. The axon line was some sort of distributed transmission line. Ion pumps are roughly voltage sources. Voltage-gated ion channels are kind of like p-n junctions. So what's like the transistor? What's going to modulate effectively the behavior that we showed before? And very loosely speaking, we can kind of think as the biological third terminal that enables transistor-like behavior is the synapse. Okay, so it connects the end of the axon to the neuron in question, and this terminal effectively controls the conductance of the postsynaptic membrane, and this therefore creates a transistor-like behavior. Now it turns out that real synapses, when you get into the nitty-gritty details, are so much more complicated and powerful than simply just a third terminal. They have a little bit of computational elements, there's a little bit of memory inside of them, and so on and so forth. So it's not really the perfect analogy, but it is a somewhat useful analogy to kind of keep in the back of your mind. So at a high level, when action potentials get generated, what ends up happening is the synaptic input somehow changes the sodium channel conductance. This means that sodium suddenly starts to flow into the cell, What this does is it causes the cell to depolarize. So normally the cell potential is, say, for example, negative. Depolarized means it goes positive. So the sodium channel opens. This creates an aggressive positive feedback cycle, which causes this huge delta V spike of voltage across the cell membrane. But then once this happens, it can't happen, forever. Otherwise, the cell will blow up, and so there's some other feedback cycle that starts to close the sodium channel, opens up the potassium channels to kind of bring that potential back down to its nominal voltage, and the cell settles back down to normal. So this is roughly how an action potential gets generated. As you can see, it's basically a spike or pulse of information. You can think of this as a pulse, as like a logic 1, for example, being sent down a transmission line. So we briefly discussed how action potentials can propagate down axons. This is just a little cartoon that basically shows how this happened. I think we're essentially nearing the end of the lecture here, so we're gonna skip this. So I just wanted to make 2 quick notes before summarizing and finishing the lecture here. What's interesting to me anyways is that synapses actually offer 2 modes of operation. There's an inhibitory mode of operation, which means as the voltage increases, the conductance or the current increases in the cell, or an excitatory behavior, whereas the voltage decreases, conductance or currents increases. So this sounds very similar to an NMOS and PMOS transistor, right? So again, it's not a perfect analogy. That the synapse is so much more complicated and powerful than just saying it's the third terminal, but there's kind of nice parallels to what's going on in our MOSFETs. Okay, now axons can be stimulated to artificially fire action potentials at will. That we can do this mechanically. Mostly we do this electrically, but we can also, in some cases, do this via light or thermal or ultrasound type of pulsation as well. So just to summarize the lecture here, we've said that biology operates and computes with a distributed hybrid analog digital computing paradigm. Very, very efficient, operates at low voltages, low currents, distributed, highly parallel. And yet, remarkably, the physics behind how these neurons do their computation is remarkably similar to how subthreshold MOSFETs work. Again, the analogy is not perfect, but it's pretty good. Okay, so as emerging electrical and biomedical engineers, I think this is a useful lesson that some of the basic building blocks that we use to construct circuits and so on are quite similar and relevant to what we'd be building our or to what we're studying in terms of how the human body works, and also understanding this will help us potentially build better interfaces. So the next few steps in the next few classes, we're going to basically switch to circuit design, and we're going to introduce basic building blocks specifically related to how to build amplifiers and current mirrors and so on when focused on subthreshold mode of operation. And then after this, we're going to get to lectures on how the heart works, and then how to build interfaces to the heart and neural interfaces, stimulators, and so on and so forth. So the rest of the class, we're going to have a lot of fun designing circuits and applying them to biomedical applications.